Okay, so let's get back to Leibniz's theorem. Remember, we're talking about series that are not necessarily non-negative series. Okay, so right. So Leibniz's theorem says that if you have a sequence is a decreasing sequence, or actually we just need non-increasing, but decreasing is fine. So if A is a decreasing sequence and the limit of the a sub n's is 0 as A goes to infinity, then the sum of -1 to the n a sub n converges. Okay, so for example, if we look at -1 to the n, 1 over n squared, and from 1 to infinity. Yes, Frank?
So an doesn't have to be a positive.
It does have to be positive. I guess that's built into it because you're saying it's decreasing down to 0. Right, so I guess I made it clear, I spelled it out last time, but it's built into these two. So if you see something like this, right, you got 1 over -1 to the n, 1 over n squared, right? These terms, these are your a sub n's, right? And you see that they are a 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, etc., etc. Yes, Hannah?
Does it have to be decreasing sequence or just non-increasing sequence?
Non-increasing is fine. Yeah. So. Non-increasing is fine. I guess that's what we mean by decreasing. If I say strictly decreasing, that means that's, yeah. So when I say decreasing, I mean non-increasing.
Okay.
Yeah. Yes, proceed. Okay. So if you see something like this, right, you can use Leibniz's test on it because these guys, these a sub n are decreasing, and you've got alternating signs, right? And so you know that this converges. Right. You know that 1 over n plus 1 squared is bigger than 1 over n squared. Okay, it's smaller than 1 over n squared. Right. It's a decreasing an plus 1 is less than an, right? Because 1 over n plus 1 squared is less than 1 over n squared. Right. So it's clearly a decreasing sequence. Okay. Okay. But we actually didn't need to use alternating series on this. Why not? We actually knew this. We actually knew that this converged already. Why? Anna? No. Chandler?
P-test?
No, it's a no. Anna?
The absolute root of partial sum?
The absolute value. So yeah, just take the wait, what?
Absolute root of partial sum?
Absolute root of partial
Like partial sum, absolute root an.
Are you saying absolute value?
It's absolutely convergent.
It's absolutely convergent. Yes, thank you. Yeah. So, right, we don't need to use alternating series on this guy because look, if you take the absolute values, you get 1 over n squared, right? Since the sum of the absolute values converges, we know that this series converges, right? So we didn't actually need to use. We don't need to use the alternating series on it. Okay. But suppose we have something like this, summation -1 to the n, 1 over n to the p, where p is, say, p is 1/2. Okay, here we've got n squared, right? Sum of 1 over n squared converges, so absolute convergence works, right? Does this series converge absolutely? No, right? Because you'd be looking at summation 1 over n to the 1/2, right? So let me just put the 1/2 there. Right? We'd be looking at summation 1 over n to the half. Well, that diverges by the p-test, right? Okay, but this thing, you can use Leibniz's test on it, right? You say, well, look, is 1 over n to the 1/2 decreasing? Sure, right? Is a sub n plus 1 smaller than a sub n? You got 1 over the square root of n plus 1. Is that smaller than 1 over the square root of n? Right? And that's certainly true, right? Because the square root of n plus 1 is bigger than the square root of n. Right? So this is a decreasing sequence, right? This is a decreasing sequence, and it decreases down to 0, right? And so this Leibniz's test says that this converges. Okay. Even though the series is not absolutely convergent, it's convergent. It's so-called conditionally convergent. Right? So it's conditionally convergent. Okay. 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 So okay. So let's see why this happened. Why does this happen? Right? Why does Leibniz's test work? Okay. Why does Leibniz's test work? So let's think like this. Right, n from 1 to infinity. Let me make it. This doesn't change anything. I'm just going to put a +1 here, just to make the picture nicer. It doesn't matter if I put this +1 or not. Okay. So what we're doing is we're looking at a1 minus a2 plus a3, right? Minus a4 plus a5, etc., right? That's the series. That's our series here. Okay, I put the +1 just to make the first guy positive. Just my preference. Doesn't matter. Okay. Okay. Can anybody say anything about the sequence of partial sums? Can anybody say anything about the sequence of partial sums? Okay, so the ANs are decreasing, right? The ANs are decreasing, and they go down to 0. For the picture, here's A1. That's the first partial sum. Okay. Draw out. Take a minute and draw on the number line where the next 2 points would be. Where would S2 be? Where would S3 be? Where would S4 be? Where would S5 be? does anybody see something that happens, see some phenomenon that occurs? What do you think?
Do they alternate on the sides of 0?
Well, no. Wait, very clear?
It stays between A1 and 0.
Okay, yeah, so, yeah, that's great. So you say, well, look, A2, we're going to subtract A2, but A2 is smaller than A1, right? A2 is smaller than A1, so we go back to some point, right? We get A1 minus A2, that's our second partial sum, right? But we don't go all the way back to 0, or at most we go to 0, okay, right? Right? And then where's S3 going to be? Well, S3 is going to be somewhere between S2 and S1, right? We go back this way, we add on A3, but A3 is smaller than or equal to A2, right? So we can't go all, I mean, at most we go all the way back to A1. Okay, so we get here's sum 3, partial sum 4, partial sum 5, et cetera, right? And the numbers are eventually, in the limit, they go down to 0, right? So they're going to be bouncing back and forth. Okay. So let me ask you to say one thing. What do you see about the odd partial sums or the even partial sums? What do you see? Observe. What do you see? Is it too obvious? Are you?
Evens are closer to 0, odds are closer to A1.
Say it again?
Like the odds are closer to A1.
The odds are closer to A1? Okay. Yeah, the odd guys are on the right-hand side, and the even guys are on the left-hand side. Right? So the odd guys are all bigger than the even guys. That's true. Right? So you've got these even guys here, and you've got these odd guys here. Right? And no even guy is bigger than any odd guy. Right? So the odds, S2n plus 1s, right? The odds are all bigger than the even guys. That's true. Does anybody see anything else about the if you just look at the odd sequence? Here's S1, here's S3, here's S5. Tanima? It's decreasing, right? And the evens are increasing, right? So S evens are S2, 4, 6 is an increasing sequence, and S1, 3, 5, etc. are a decreasing sequence, right? And further, the distance between them, right? If I look at S2n plus 1 minus 2n, right? If I look at the distance between them, well, that's going to be the last term, right? It's going to be an plus 1. So further, the distance between them goes to 0. Okay, so why is it true that in Leibniz's test the alternating sum converges? Well, look at the sequences of partial sums. These guys are an increasing sequence, and they're bounded above by A1. These guys are a decreasing sequence, bounded below by 0, right? So both of these things converge, right? It's a monotonic sequence that has a bound. This guy's a monotonic sequence that has a bound, right? So the sequences, the odd partial sums and the even partial sums both converge, right? Further, the difference between them goes to 0, so they converge to the same number. they converge to the same number, well, that tells you that the full sequence of partial sums converges to some number. So your sequence converges, your series converges. Yeah, Frank.
So shouldn't it be A sub 2?
Oh, I'm sorry. Yeah. Okay. So this is the idea. This is the idea behind the alternating sequence theorem, behind Leibniz's theorem. Right? If you've got a decreasing sequence, and you sum them with alternating signs, well, it's going to start bouncing in. It basically bounces back and forth like this, and will tend towards a limit. Okay, so I'll go over this again. So I've sort of written it out, sloppily now. I'll write it out again at the beginning of class next time. Oh my God! So so I have the exams.